Hello friends, myself Nalinkanta Jana, Senior Lecturer in Physics, Bharuneswar Mahavidyalaya, Utkal University. Our today's topic is resonance. Here we have to discuss what is resonance, under what condition resonance occurs, what is resonant amplitude or amplitude of resonance, velocity resonance, phase resonance, sharpness of resonance, all these. Today we have to discuss all these factors regarding resonance. So, before going to the details of these factors, let us first know what is resonance. Resonance is a phenomenon of setting a vibrating body into undamped oscillation under the action of a periodic force in which the amplitude becomes very large. And this situation occurs when the frequency of the applied force coincides with the frequency of the body, that is the natural frequency of the body. And at this situation, the amplitude ideally becomes infinity. That means theoretically the amplitude of a vibration becomes infinity at resonance, and actually this situation never happens. Only in resonance the amplitude becomes very high. So, let us calculate the amplitude of resonance. What we know in our previous discussion, in forced oscillation, the amplitude of oscillation is found to be A is equal to F0 by m into root over of k4 k square p square plus p square minus omega square, where omega represents the angular frequency of the vibrating body and p represents the angular frequency of the applied periodic force. So, from this we can conclude that this amplitude will be maximum only when the denominator will be minimum, and this denominator will be minimum or a constant value when its derivative becomes 0. That means its variation becomes 0. So, to get maximum amplitude, that means to have the denominator to be minimum, let us find out the variation of this denominator with respect to p. That means we have to find out the derivative of the denominator with respect to p. For amplitude to be maximum, the denominator of above expression should be minimum. And d by dp of 4 k square p square plus p square minus omega square whole square should be 0. Hence, we can write here as, by differentiating this we get 4 k square into 2p plus 2 into p square minus omega square into 2p equal to 0, which implies 8 k square p plus 4 p into p square minus omega square equal to 0. Now taking 4p as common, we can write 2k square plus p square minus omega square is equal to 0. But this p is not 0 because it is the angular frequency of the applied periodic force. Hence, this bracketed term will vanish. Now, this p is not 0, so the bracketed term will vanish. To justify this equation, hence we can write 2k square plus p square minus omega square is equal to 0, implies as p square is equal to omega square minus 2k square, implies as p is equal to root over of omega square minus 2k square. Now A max will be equal to how much? F0 by m into root over of 4k square into p square, and the value of p square is omega square minus 2k square plus p square minus omega square is equal to minus 2k square whole square, and expanding this we can write F0 by m divided by root over of 4k square omega square minus 8k fourth plus 4k 4, which is equal to F0 by m whole divided by root over of 4k square omega square minus 4k fourth, which is equal to F0 by m divided by 2k taken outside. So, within it will be omega square minus k square, omega square minus k square. Now, the expression for A max will be A max is equal to F0 by 2k m root over of omega square minus k square. This is the expression for the amplitude maximum or the resonant amplitude, that is the amplitude of the vibrating body at resonance. Special case: if there is no frictional force, if there is no frictional force, then k is equal to 0. So A max, that is the amplitude of the vibrating body at resonance, will be equal to F0 by 0 into root over of omega square minus 0, which is equal to infinity. That is, ideally or theoretically the amplitude becomes infinity at resonance. But this situation never happens because k cannot be 0. That means some frictional force exists. So, k cannot be 0, hence A max cannot be infinity, but theoretically A max will be infinity at resonance. Now, from this expression we can also calculate the frequency of a vibrating body at resonance, from which it will be easy to calculate the time period of the vibrating body at resonance. Let us calculate first the frequency of the vibrating body at resonance, and is termed as the resonant frequency. Okay, we know that P square is equal to omega square minus 2 k square, implies as P is equal to root over of omega square minus 2 k square. So, which implies as P is the angular frequency of the applied periodic force, and hence this can be written as 2 pi nu, which is equal to root over of omega square minus 2 k square, implies as nu is equal to 1 by 2 pi root over of omega square minus 2 k square. This is the expression for the frequency of the vibrating body at resonance. Now, we know the time period is the reciprocal of frequency. So, in terms of time period, this expression can be written as, implies as 1 by t will be equal to 1 by 2 pi root over of omega square minus 2 k square, implies as t will be equal to 2 pi divided by root over of omega square minus 2 k square. This is the expression for the time period of the vibrating body at resonance. Okay. We have discussed resonance, amplitude of resonance, and expression for amplitude, and expression for maximum amplitude, that means amplitude at resonance, from which we came to know that ideally the amplitude becomes infinity at resonance, but this situation never happens. And also from this experiment, from this expression we have found frequency of oscillation and also the time period of a oscillation. And you must have known the practical examples of situations where resonance may happen, that the soldiers are warned not to march while passing over a suspension bridge. The soldiers are warned not to march while passing over a suspension bridge, because during marching over a suspension bridge, the soldiers apply a regular periodic force on the bridge, which has its own frequency P, and the bridge also has its own natural frequency omega. If there is no frictional force, then from this condition we can know that k will be 0 and p square will be omega square. That means at a resonance p is equal to omega. That means if by chance the frequency of the applied force given by the soldiers during their marching is exactly balanced or coincided with the natural frequency of the bridge, then resonance will occur. And at that situation, the amplitude will become infinity, for which there is a chance of collapsing of that bridge. Hence, the soldiers are warned not to march while passing over a suspension bridge, just to avoid the situation of occurrence of resonance. Also, the other practical examples of resonances are while we are tuning our radio receiver set or television set for a particular channel, then what we do? Every channel has its own natural frequency, and we, by tuning the set, apply another frequency. If our supplied frequency coincides with the natural frequency of that channel, then there will be resonance, for which the amplitude will be more, and hence we will be able to see or listen that channel in our television set or in our radio receiver set. There are also other cases of resonance. That means you must have felt in a crowded area there is a large sound produced by the people, but nobody is shouting, everybody is talking with its own natural slow voice, but due to gathering their natural frequencies almost coincide with the frequency of other vibrating bodies, for which resonance occurs. Though it is not an ideal case, it is the practical case. The sound becomes louder, and we feel that in a crowded area everybody is shouting, but nobody is shouting, and this situation happens only because of the occurrence of resonance. Let us know what is sharpness of resonance. Our topic is sharpness of resonance. What is sharpness of resonance? Sharpness of resonance represents the rapidity with which the amplitude falls due to an increase in p square minus omega square. Sharpness is the rapidity with which the amplitude falls due to an increase in p square minus omega square, where p represents the amplitude, p represents the angular frequency of the periodic force and omega represents the natural frequency of the vibrating body. To know the sharpness of resonance, we have to know the amplitude and the amplitude of resonance, that means the maximum amplitude, because sharpness of resonance is nothing but the ratio of AM x, that is amplitude maximum, divided by the amplitude of oscillation. Sharpness of resonance is equal to the ratio of amplitude maximum and the amplitude of oscillation. Already we know the expression for amplitude of oscillation is this much, and the expression for maximum amplitude is this much. Now, putting these values here, we can write sharpness of resonance as A max by A, which is equal to F0 by 2 k m root over of omega square minus k square divided by F0 by m into root over of 4 k square p square plus p square minus omega square whole square. Now, simplifying these two, we can write sharpness of resonance is equal to A max by A, which is equal to root over of 4 k square p square plus whole square of p square minus omega square divided by 2 k m root over of omega square minus k square. M get cancelled. If we omit the root overs, that means taking the square of the numerator and the denominator, we can write this as 4 k square p square plus p square minus omega square whole square divided by 4 k square into omega square minus k square. But we know that this omega square minus k square is nothing but p square. So, here we can write this as 4 k square p square plus p square minus omega square whole square divided by 4 k square p square, which can be written as writing this 1 plus p square minus omega square whole square divided by 4 k square p square implies A max by A whole square is equal to this much. So, implies A max by A whole square is equal to 1 plus, let us write this as delta by 2k whole square into omega square, where delta is equal to p by omega minus omega by p. And from this, we can conclude that the sharpness of resonance depends on the value of delta by 2k. From this, we can conclude that the value of sharpness of resonance depends on the value of delta by 2k. Let us take the case of a graphical representation of the sharpness of resonance. This case represent ideal case of resonance. This is the case of low damping. This represents medium damping, and this one represents large damping. Here we have shown this is the ideal case of resonance, and these are the cases of damping. Here the damping is very large, hence the sharpness is very small, and this is the case of low damping. Okay. Now, we will discuss velocity resonance. Okay. Let us discuss velocity resonance. That means velocity at resonance. Resonance occurs when the frequency of the applied force coincides with the natural frequency of the vibrating body, and at resonance the amplitude is maximum, and consequently the velocity of the vibrating body will also be maximum at resonance. Hence, to get the expression for the velocity at a resonance, let us first calculate what is velocity resonance. So, velocity is equal to V is equal to F0 by R, which is equal to F0 divided by root over of R square plus MP minus 1 by PC whole square, because previously we have discussed that this R is taken as R cos theta and this MP minus 1 by PC whole square is taken as capital R sin theta, from which we get R is equal to this much. But while we are discussing about the forced oscillations, we have taken R is equal to 2 km and 1 by C is equal to S is equal to omega square m. So, putting the values of small r and 1 by C in this expression, we can write V is equal to how much? F0 divided by R square, that is root over of square of 2 km plus MP minus 1 by PC, but 1 by C is S and that is omega square m. So, it will be omega square m by P whole square. The velocity will be maximum when the denominator of this expression becomes minimum. But we know the velocity will be maximum at resonance. So, to get the velocity resonance, that means to find out the expression for the maximum velocity, we have to make this denominator minimum, and this denominator will be minimum when this factor becomes 0. The derivative of this factor becomes 0. That means the variation of this factor with respect to P becomes 0. So, to get the maximum velocity, we have to differentiate the denominator with respect to P and equalize to 0. Okay. For velocity to be maximum, the denominator of the given expression for velocity should be minimum. And hence the derivative of this with respect to p will be equal to 0. Here is the square of m, and if it is in the square, so m will be taken outside and m is constant, and by taking outside we can write this as m into d by dp of 2k plus p square minus omega square by p whole square equal to 0. Since m is not equal to 0, hence since m is not equal to 0, hence these factors becomes 0, implies as d by dp of 2k whole square plus d by dp of p square minus omega square by p whole square is equal to 0. But 2k both are constant, so this becomes 0, implies as 0 plus d by dp of p square minus omega square by p whole square equal to 0, which implies as d by dp of p to the power 4 plus omega to the power 4 minus 2 p square omega square by p square equal to 0, implies as d by dp of p square plus omega to the power 4 by p square minus 2 omega square is equal to 0, implies as taking the derivative we can write this as 2p plus omega 4 into minus 2 by pq minus 0 equal to 0, implies as 2p minus 2 omega 4 by pq is equal to 0, implies as 2p4 minus 2 omega 4 by pq equal to 0, implies as p4 minus omega 4 equal to 0, implies as p4 is equal to omega to the power 4, implies as p is equal to omega. This is the condition at which the velocity becomes maximum, that means velocity resonance occurs. From this we can conclude that velocity resonance occurs only when the angular frequency of the applied periodic force is exactly balanced by the angular frequency of the natural frequency of the body. That is, velocity resonance occurs when the frequency of the applied force coincides with the frequency of the vibrating body. So, putting this condition in the expression for velocity, now we can get the maximum velocity as, now putting this condition in the expression for velocity, we can get the expression for maximum velocity or velocity max. So, V max is equal to F0 divided by 2 km. This is velocity resonance. Now, as we are discussing about resonance, amplitude resonance, sharpness of resonance, velocity resonance, also we have calculated frequency resonance and a time period at resonance. One term is remained back, that is phase. So, we should calculate the phase resonance. That means the phase of the vibrating body at resonance. Okay. We have to now discuss what is phase resonance and we have to derive the expression for the phase resonance. What is phase resonance? First we should know what is phase. It is the characteristic of a vibrating body which describes the position and configuration of the vibrating body at the instant we consider. That means phase represents the position and configuration of the vibrating body at the instant we consider. Okay. To calculate the phase of a vibrating body at resonance, let us first write the expression for phase. And already while we were discussing about forced oscillations, we had taken small r as capital R cos phi and MP minus 1 by Pc is equal to capital R sin phi. And from this we can write tan phi is equal to R by MP minus 1 by Pc. 1 by C is nothing but S. So, this can be written as R divided by MP minus S by P, which can be written as, taking the LCM, we can write here MP square minus S and this P will be taken outside. So, it will be R P divided by MP square minus S and dividing by M, we can write this as R P by M divided by P square minus S by M. At resonance, but at resonance omega square is equal to P square, which implies omega square is nothing but S by M and this is equal to P square. So, this implies P square minus S by M is equal to 0. Putting this value in this expression, we can write tan phi equal to Rp by M divided by P square minus S by M, but we have found P square minus S by M equal to 0. So, putting the value of 0 here, we can get something by 0 is nothing but infinity. So, this becomes infinity, but tan pi by 2 is nothing but infinity. So, comparing these two, we can write tan phi is equal to tan pi by 2 implies as phi is equal to pi by 2. Hence, we can conclude that the phase of the vibrating body at resonance is pi by 2. That means, when the phase of a body becomes pi by 2, then resonance occurs, and at this stage your omega square is equal to p square. Now, cases arise. Now, 3 probable cases arise, such as number 1, for P is equal to omega implies as P by omega is equal to 1, for which implies as phi becomes pi by 2. Number 2, for P by omega greater than 1, phi is also greater than pi by 2. And the third case, for P by omega less than 1, phi becomes less than pi by 2. These are the probable cases of the phase with the relative variations of the angular frequency of the applied force and the angular frequency of the vibrating body, but resonance occurs only when P is equal to omega, and at this stage P by omega becomes 1 and the phase becomes pi by 2. That means, when the phase becomes pi by 2, resonance occurs, and this is known as phase resonance. Okay friends, here we have discussed resonance, amplitude resonance, velocity resonance, sharpness of resonance, frequency resonance, time period at resonance, and also the phase resonance. And here we finish the topic resonance. Many thanks.